Okay, thank you. Good morning to everyone. My name is Leopio D'Adderio, and I'm a member of H SAF Precipitation Cluster. This morning I want to talk about the products H68 and H67, which are the two H SAF Level 3 microwave-based precipitation estimation products. First of all, I want to thank my colleague here at the Institute of Atmospheric and Climate Science of National Research Council in Italy, here in Rome, for the precious collaboration and contribution. What we'll see today, so we'll start with the definition of the level 3 product, and we also see the difference with respect to level 2 and level 1. And then we'll move to the H68 product with an overview of the product, and then with an algorithm description of the product. We also see some examples. We'll do the same for H67. So, as I said, an overview, the algorithm description, and then some examples. We'll conclude this presentation with the current status of the products and future perspectives. So what is a level 3 product? A level 3 product is a geophysical product with spatial and or temporal integration. So you can use different products, type of data orbits to provide a level 3 product that can be global or integrated over different time interval with respect to the original level 1 data. Usually these products are have a large timeliness or offline. On the other hand, a level 2 product is always a geophysical product, but it's derived from the corresponding level 1 product. So it has the same spatial resolution and generation frequency of the level 1 product. So it implies that one segment or the whole orbit of level 1 products is used to provide a level 2 product. Usually these products are provided in near real time. And finally, a level 1 product provides calibrated and georeferenced data. So EUMeTrain divides the level 1 products in 1A, which is georeference. It means that the location of the measurements is known. 1B, where the data are calibrated, and 1C, where the data are gridded. So, for example, the Meteosat second generation level 1 data are 1C because they are both gridded and calibrated. So let's start with the H68 product. First of all, I want to specify that H68 is the product ID, but we are moving to identify the product with the acronym, which is P-IN-PWM, which basically means precipitation instantaneous from a passive microwave. So, as the acronym suggests, the main output is the instantaneous precipitation rate. The product is provided on a regular grid, 0.25 by 0.25 degrees, over what we call the HSAF extended area, which means between 60 degrees south to 75 degrees north, and between 60 degrees west to 60 degrees east. And it's provided every 30 minutes, so the temporal resolution is 30 minutes, and it is based on 3 main modules: the Remapping Module, the Adjustment Module, and the Merging Module. And we'll see these modules later in the presentation. So why a user should prefer H68 product? basically because it summarizes all the available microwave-based level 2 precipitation rate products in a single estimation. So the precipitation is given. The precipitation rate is given on a regular grid whenever it is possible. It means where the grid box is covered by at least one satellite. It has a quite good temporal resolution, and it is a near real-time product because it is provided within 4 hours with respect to the considered half hour. And this product will be an input for future precipitation products like the MTG-based precipitation estimation products. And finally, the format of the output is easy to read because it is an XCDF file. So this is the block diagram of the H68. So we have 5 input products identified by H01, H02B, H18, and from the auxiliary products H17 and H20. These are all level 2 products, which are the input of H68. So we consider the variables provided by these level 2 products, and what we do, we remap. First of all, we do a data regrid. So we remap the orbital data on the regular grid, as I said, 0.25 by 0.25 degrees. Then we adjust the remapped precipitation rate by intercalibrating the input products with respect to a reference, which is the combined DPR-GMI product of the GPM mission, and then we merge the data, considering taking into account the number, the type, and the characteristics of satellites overpassing each grid box. We do this for the instantaneous precipitation rate, and we do this also for the quality index and for the precipitation phase. So the output variables, as I said, are the instantaneous precipitation rate over regular grid 0.25 by 0.25 degrees, the phase of precipitation, the quality index, and also the number of conical and cross-track satellite overpasses each grid box, and also their sum. And the data format is, again, an XCDF file. Let's have a quick look of the H68 input products. As I said, 5 products. On the first column, you can see both the acronym, the product ID, and also the instrument from which they are derived. So basically, we have 3 products derived from conical scanner sensors, and 2 from cross-track scanner sensors. And 3 of these are based on a neural network approach, and 2 of these are based on a Bayesian approach, so it's a more physical approach. So, as I said, the algorithm is based on 3 modules. So the first one is the remapping module. The remapping module works on the orbital data of the H68 input products, and it is based on bilinear interpolation. So basically, we move, as the example here shows, both the examples, we move from orbital resolution to a regular grid resolution. For instance, you can see that the auxiliary H20 move from higher resolution to a lower resolution, but on the other hand, H18 moves from lower resolution to a higher resolution, depending also from the position of the pixels in the slot. Then we have the adjustment module, which runs just after the remapping module. Its aim is both to improve the coherence and decrease the discrepancies among the H68 input products. So what we did, we derived a power law to move the precipitation rate provided by level 2 products to an adjusted precipitation rate. After that, this power law is applied to each H68 input product. The power law is obtained taking as reference 5 years of coincident measurements between every H68 input product and the to-be combined precipitation rate. So more specifically, the to-be combined precipitation rate is upscaled through the same linear interpolation on the same 0.25 by 0.25 degree regular grid, and the coincident measurements are matched up, and the power law is derived. Here you can see an example of the two-dimensional histogram between H01 and to be combined taken as a reference before the adjustment module on the left and after the adjustment module. So we have more samples on a one-to-one line, and we lose most of the overestimation at low to be combined precipitation rate values. And the improvement that the adjustment module provides is certified by the root mean square error that decreases from 346 to 2.19 millimeter per hour. But what is the to be combined precipitation rate product, and why did we choose this product as a reference? So the to be combined precipitation rate product, as the name suggests, combine the information from active and passive microwave sensors on board of core observatory of GPM Global Precipitation Measurement mission. The active sensor is the DPR, the first dual frequency precipitation radar on board of a LEO satellite. It has an Ku and Ka band radar, and it provides a three-dimensional retrieval of the precipitation structure with a 5 kilometer of spatial resolution. This is horizontal spatial resolution because the vertical spatial resolution is even higher. On the other hand, the passive microwave sensor is the GMI, the GPM microwave imager, which is a conical scanning radiometer with 13 different microwave channels and with different spatial resolution ranging from 6 by 4 kilometers square to 31 by 19 kilometers square, depending on the channel frequency. These are the most advanced active and passive microwave sensors on board of a LEO satellite. So the final module is the merging module, which runs after the adjustment module and performs an ensemble mean of the all data produced by the H68 input products in the previous 30 minutes. After that, these products are remapped over the 0.25 by 0.25 degree regular grid and adjusted with the adjustment module. The merging module consists of three main steps. The first one is the derivation of a ranking for each satellite type. So we have a ranking for the conical scanning satellite, and one for the cross-track satellite scanning satellites, as you can see on the table here on the right. And the ranking takes into account the characteristics of the sensors and the pixel-based quality flag associated to each satellite. Then the microwave precipitation products are sorted according to the ranking of the table in the previous slide. And finally, the two best microwave precipitation products, one for the conical, one for the cross-track, of course, if they are available, are averaged to provide what we call the optimal instantaneous precipitation rate for each grid box. And we do the same also for the quality index and for the precipitation rate. But let's see an example to better explain this merging module. So consider this plot on the right, where you have the number of the satellites overpasses the H SAF extended area in given 30 minutes. So you have grid boxes with one satellite, the blue points, grid box with 2, 3, and up to 5 satellites. So what the merging module does. So if you have one satellite, it's very easy. The precipitation rate is taken from the corresponding product. If you have two satellites, you have three possible scenarios. So if both satellites are conical, the precipitation rate is taken from the best ranked in the conical ranking. If both are cross-track, the same. The precipitation rate is taken from the best ranked in the cross-track ranking. But if you have one conical and one cross-track scanning satellite, you do the average of these two values. If you have 3 or more satellites, you have more and more possible combination. For instance, with 3 satellites, you can have 2 conical, 1 cross-track, so you get the best conical and the average with the cross-track. On the other way, if you have 2 cross-track, 1 conical, you get the best cross-track and the average with the conical. And so on if you have 4 or 5 or more satellite overpasses a grid box. So these are some examples, output examples of H68. So you can see both the total count, so the number of satellites for each grid box, or passes each grid box in a given 30 minutes, and the corresponding precipitation rate for these 2 half hours considered here. So you can see the advantage of H68. For instance, consider that you have a precipitation system covering this area in the southwest of this map. So if you want to analyze this system, you should get 3 or 2, depending on the grid box, different products, level 2 products. But with H68, you have only one estimation. After that, the level 2 are adjusted to move to a very similar precipitation estimation. In the plot on the bottom, you can see some statistics which report how often you can have 1, 2, and 3 or more satellite overpasses a grid box in 30 minutes. You can see that most of the grid box are covered for most of the time by one satellite, and you can have 2 and 3 or more satellites with a significant probability at very high latitudes. So now we can move to H68 product. Again, the acronym in this case is P-DM-PMW, and the main output of this product is the 24 hours mean precipitation rate. It is always provided on the same areas, on the same H SAF extended area, and on the same 0.25 by 0.25 degree regular grid. It runs four times per day at 0, 6, 12, and 18 UTC. And it is based on the one main module, the ensemble main module. So this is the block diagram of H68. The input product of H68 is of H67 is H68. And after the ensemble mean of the gridded alpha hour instantaneous precipitation rate, the output variables that H67 provides is the 24 hours mean precipitation rate, the 24 hours maximum precipitation rate, the total number of alpha hours covered by at least one satellite, and the 3 hourly number of half-hour intervals covered by at least one satellite, and also the quality index of the data. Again, the data format of the output file is always in XDF. So very quickly, the ensemble module runs 4 times per day, as I said, and its averages the valid precipitation rate estimate out of 40 half-hourly outputs produced by H68 over 24 hours. And you can see also the additional output that we already specified in the block diagram. Just to better explain, the quality index provided takes into account the number of useful alpha hours. It means the number of alpha hours where there is a valid measurement, the latitude of the grid box, and the position of each satellite product based on the ranking provided in the H68 algorithm. Here are some examples, because H67 is particularly recommended to monitor long-lasting precipitation events. Here we have the cyclone Idai occurred on the Mozambique Channel between March 10 and March 18, 2019. In this plot, we can see the daily evolution of accumulated precipitation from March 11th to March 14th, and you can see both the moving of the precipitation system and also the amount of precipitation provided by H67. This is another example of the flood occurred in Sardinia very recently, last 28 November. We can see that the number of overpasses over the whole H SAF area, and the zoom for the considered area with the associated the mean precipitation rate and the maximum precipitation rate on the plots here on the right. And this is the situation for the same day on the whole H SAF extended area. both for the mean precipitation rate and the maximum precipitation rate. But are these two products H68 and H67 operational? Not yet. They are both in pre-operational mode, and it is expected to become operational during the next spring-summer season, maybe more summer, so 2021. What does it mean, pre-operational mode? It means that they are under EUMeTrain review process, so the ATBD, the algorithm theoretical basis document, is already approved, and we are waiting for the operational readiness review, which is estimated during spring 2021. But pre-operational mode means also that it's possible to have data of both products, of course, upon request. So if you are interested in analyzing some particular case study, you can ask the data, and we are also testing H68 and H67 for some interesting case studies, also to check the reliability of these two products. And what will be the evolution of these two products? First of all, there will be the extension from H SAF extended area to a global coverage, and H68 will be an input to the next day 2 MTG-based product based on a machine learning approach. And H67, on the other hand, will be an input to the precipitation soil moisture integrated product, H64. You can follow the presentation of our colleague Luca Ciabatta in the afternoon session and at 13 UTC. And also the upcoming global level 2 precipitation products, including the EPS second generation products that you can see on the table below, will be integrated in H68 and consequently in H67 products. And just to conclude, here you can find the references for each algorithm of the level 2 products used as input of H68 and of course H67. So if you are interested to learn more about the algorithm, you can download these papers. So thanks for your attention, and if you have more questions or information, you can contact me, or you can visit the HSAF website or HSAF Twitter account.